This is Unit 8, Lesson 6, and we're going to be learning how to graph our first type of rational function. This one is called the reciprocal function. So first thing we're going to do, just like every time we learn a new function, is we are going to graph the parent function and then talk about how we can transform it. So the parent function is f of x equals 1 over x. That's the simplest version. That's why we call it a reciprocal, because it flips the x into the denominator, just like a reciprocal function does. So here it is on Desmos. So I've got it typed in. So this is 1 over x, and this is what our graph looks like. So I'm going to lower this down so we can take a look. So see, it just kind of curves along right here. It glides right along the y-axis and then turns and glides right along the x-axis, and then it does kind of like a kitty corner shape over here. So a couple points you want to look. It does have a point right there at 1, 1. It's got another point there at -1, -1. So you can see it's got a point right there, it's got a point right there, and then it just kind of glides along these lines, curves, and then glides along this line right there. And remember, something that it gets really, really close to but doesn't actually cross, that's called an asymptote. So you'll see over here, we'll talk about the asymptote. So this shape is called a hyperbola. Those two kind of boomerang shapes that occur opposite to each other, that's what we call that. The domain is almost everything except for this one x value right here. That's what asymptotes do. It can be anything except for that one value. Same thing with the range. Look at this y value right here. It gets really close to y, but it never actually hits it. So we can say y can be anything except for 0. So that's the vertical asymptote. The vertical asymptote is that one x value that it's not allowed to equal. So we can say x equals 0 is a vertical asymptote. And if we wanted to, we could put a little dotted line right here that we aren't allowed to cross over. Same thing with the horizontal asymptote. We could say that's y equals 0, so that's this dotted line right here that we're not allowed to cross over. All right, so that's just the original one. We'll talk about the transformations. And this section should be pretty quick because it's the same transformations that we make with every single type of graph. So the standard form is this. A stands for like a multiplier. With the x, we have a minus h, and then after the whole thing, we have a plus k. So the a, the h, and the k, we've used these things many, many times before. So remember, h is the horizontal shift, and k is the vertical shift, just like every type of graph we've ever transformed. And then remember, with horizontal, the left and right is actually kind of opposite of what you'd think it would be. Plus actually shifts your graph to the left, minus shifts to the right. But then with the vertical shift, plus minus does what you'd think it would do. So plus actually does shift you up, and minus actually does shift you down. And then a, if a is negative, then it flips the whole thing upside down. We call that a reflection. We say it's reflected, I guess, across the x-axis. And then if this value is larger or smaller than 1, it ends up being a stretch or a compression. So that whole section is just the exact same section that we've done with every type of transformation. We did that with square roots and cube roots and logs and exponential graphs. A long time ago, we did it with parabolas. So we've done this whole transformation thing many, many times. This, we've got one additional feature, the vertical asymptote and the horizontal asymptote. So the vertical asymptote originally was 0, but if we shift our whole graph either to the left or to the right, that asymptote is going to go with it. So if we shift to the left or the right h units, the vertical asymptote will move over to x equals h. And then same thing with the horizontal asymptote. Initially, it was just y equals 0, but if the whole graph moves up or down this many units, then the horizontal asymptote will go with it. So it will just be y equals k. So when we're plotting, starting in the next page, we're actually going to begin with these features and then work from there. So writing our new functions, these are our transformations. So they're going to tell us the transformations, and then we are going to create a function. So this is a reciprocal parent function. It's reflected across the x-axis, translated 4 units to the right and 3 units down. So we can start with our f of x equals, so it's reflected across the x-axis, which means this is going to be a negative number. They don't say anything about a stretch or a compression, so we're just going to assume it's a -1. X minus h, it's translated 4 units to the right, so to the right means we do a minus, so it'd be an x minus 4 down in the denominator, and then 3 units down would be a minus right here. So 3 units down would be -3, like that. So that is what our equation looks like. We also are going to write the asymptotes. So we can abbreviate VA for the vertical asymptote. So that's just whatever x equals h is. So if we move 4 units to the right, the asymptote moves over to 4 as well. And then the horizontal asymptote, if our whole graph moved 3 units down, the y value moved down 3 units as well to a -3. Okay, so let's do that again with both of these. Reciprocal parent function is vertically stretched by a factor of 2, so that's going to be a, that will go right here. Translated 7 units up would be right here, and 1 unit left, that would be right here. So write the parent function, start with the stretch of 2, that becomes my numerator. 1 unit left would be a plus in the denominator, so 1 unit left would be an x plus 1. 7 units up would be a plus 7 after the fraction. And identify our asymptote. So the vertical asymptote, we move 1 unit to the left, so that would be x equals -1. So see this, if this is x plus 1, your vertical asymptote is a -1. If this is x minus 4, your vertical asymptote is x equals 4. You're really just taking that and setting it equal to 0. That's how you get your vertical asymptote. And then the horizontal asymptote is just the number that's on the end here. So -3 plus 7 means it would be y equals 7. So one more of these for number 3 in a slightly different format. It says it has a vertical asymptote at -2 and a horizontal asymptote at 5. So write an equation that could represent this function. So we have f of x equals the vertical asymptote is at x equals -2. So in the denominator, I know I'm going to have an x plus 2. And then a horizontal asymptote at 5, so I know I'm going to have a plus 5 right here. Now it just says write an equation, so this numerator really could be anything. Let's just keep it nice and easy and make it a 1. All right, so we know what the horizontal and vertical asymptote are, and so we can just create what we can assume the A would be. All right, so let's look on the next page, and we're going to do a few of these graphs. We're just going to do the odd graphs on the next page. So starting with number 5, we've got 1 over x plus 3. So I'm going to walk you guys through our method that we're going to use. Very first thing we're going to do is identify the vertical and horizontal asymptotes so we can sketch those in, and then we'll talk about how to get more points. So in this one, our vertical asymptote, see the denominator x plus 3? That means our vertical asymptote is at x equals -3. So I'm going to start there. 1, 2, 3, and we can put this dotted line right down here. Horizontal asymptote is always this number on the end right here. And then since there's nothing there, we just say that that's a 0. So it didn't move up or down at all, so our horizontal asymptote is just right here. So we know we're going to have these little boomerang shapes in the corners, so let's find out where those boomerang shapes are going. Domain and range is pretty easy. It's just kind of the opposite of the asymptote. So my x-coordinate can be anything except where that dotted line is, and my y values can be anything except where that dotted line is. So we're going to create a table, and what we do, it's actually a pretty easy table. We center it at the vertical asymptote, so -3 is where the vertical asymptote is, and we just want to plug in one number before and one number after. And that's it, just to get an idea of like, is there a flip, is there a stretch, is there a compression? So we're going to plug this -4 in right here for x. So -4 plus 3 means my denominator is a -1, and I have 1 over -1, which is -1. And then this, I can plug in a -2. -2 plus 3 is 1. 1 over 1 is just 1. So that's all you do. You just plot those 2 points and then just use what we know the shape looks like to fill in the rest. So -4 and -1 would be right here. And -2, +1 would be right here. And we know the way the asymptotes work. We can see that point. So we just go right along the dotted lines, curve through to hit this point, and then right along the dotted lines here. We know there's supposed to be that sort of boomerang shape. So really all we need is, whoops, crossed over the line there. Really all we need is just one point to see if there's a stretch and which corners it's going to be in, because it might be in these 2 corners, but it also might be in these 2 corners. All right, let's look at number 7. Start with our vertical asymptote. We have an x minus 2, so that means our vertical asymptote is at x equals +2. And I can put that dotted line right here. Horizontal asymptote comes from this number right here. So I have a -2 at the end. That means y equals -2 would be my horizontal asymptote. And so that is this dotted line right here. My domain and range are super easy. X can be anything except the dotted line. and y can be anything except the dotted line. Next, we just make that quick little 3-value table. So my vertical asymptote always goes in the center, and then all I need is just 1 point before it, 1 point after it, just to see what effect that stretch has. So sub in 1, 1 minus 2 is a -1, 3 over -1 would be a -3, and then minus 2 would be a -5. And then 3. 3 minus 2 is 1, 3 over 1 is 3, and 3 minus 2 is 1. So plot those 2 points. 1, -5 would be down here, so you can see that stretch takes it down a little bit lower. And then 3, 1, 3, 1 would be right here. So we curve along this point right here. This one's gonna start curving a lot faster than the previous one did. See how there's a bigger gap right here than there is right here? That's because of the vertical stretch. That's what that stretch does. It pulls it away from that inside. So it makes it look like it's farther away from that little corner. See, these are much farther away than these are, and that's because of the stretch. All right, one last problem with number 9. See our denominator, we have an x minus 5, so our vertical asymptote would be x equals 5, and that means our domain would be anything other than 5. Then we have this plus 3 on the end here. Plus 3 on the end means my horizontal asymptote is 3, and my range, y, can be anything other than 3. So let's put those dotted lines in. So x equals 5 will be right here. Y equals 3 will be right here. We already did the domain and range. And finally, one last thing, we're going to make our little 3-point table. So we have x and y. 5 is the vertical asymptote that goes in the center of my table. And all I want to see, just so I know what the shape looks like, is just one value before the vertical asymptote and one value after the vertical asymptote. So let's plug that 4 in. 4 minus 5 is -1. -1 over -1 is +1. And then plus 3 would be 4. So that's 1 point that I can plot right here. And then 6 minus 5 is 1. -1 over 1 is a -1. And then when I add 3, I get 2. So that 6, 2 goes right here. So notice these ones are opposite from these ones right here. They're in the opposite corners, and that's because of this -1. So that's what the reflection does, is it flips them to opposite corners. So connect the dots right here, use those dotted lines as a guide, and this is what our hyperbola looks like for number 9.